Okay, so I'm posting a lot of solutions here because this whole technique is critical to the rest of the chapter. So this is problem number 11, and what we're looking for is the indefinite integral of x cubed times x to the fourth plus 3 squared dx. So this is what we call u substitution. And the u is usually, just like when we did derivatives and using chain rule, it's usually the terms in the parentheses if there is a term. So we're going to say u is equal to the term in the parentheses. And then we calculate the derivative of that, but we do it as a differential. So u becomes du. And then what we do is we take the derivative of this term, just like we normally do. We have 4x cubed. This goes to 0, so we just get 4x cubed. And then we add a dx on the end of it. And then we look at the original equation and say, do we have, outside of the parentheses, do we have 4x cubed dx? Well, we don't exactly. If the only difference is a constant, then we're in good shape, because what we can do is we can divide by that constant outside, and we can multiply by that constant inside. So when we multiply 4 times the fourth, we get 1. And then we have x cubed. Then we have the term in the parentheses. And then we have the dx term. Notice I'm putting these terms in red because those match up with that. And this term matches up with that. So then we do this u substitution. So what we end up with, the 1/4 stays the same outside the problem. 4x cubed dx, 4x cubed dx just becomes dx. And the term in the parentheses is u. So we get u squared times d, actually that's du, not dx, so this should be du. Okay, because du is equal to 4x cubed dx. And now we go from something that we don't have the integrals of to something we do have the integral of. That's just a power rule, where n is equal to 2. So if we integrate this expression, we get u cubed, we add 1 to the exponent, divided by the new exponent. And then we add a constant onto the end of the whole thing. So that's not quite finished, because it's like when we did differentiation using the chain rule, we always have to make the substitution back in. So we go back up and look at what we set u equal to up here. So the final answer is 1/4. Actually, let's go ahead and multiply 1/4 by 1/3. These are both in the denominator, so we get 1/12 times u cubed, but u is x to the fourth plus 3, so that's what's cubed, and then we add our constant. We can always check to make sure this is correct by taking the derivative of this, which would be 3 times the 12th, which would be 1/4 times x to the fourth plus 3 squared, because you reduce that by 1, then use the chain rule to take the derivative of what's inside here, which would be 4x cubed dx. Well, the 4 would cancel out with the 1/4 that we got here, so we'd end up with just a coefficient of 1. We have x cubed when we take the derivative inside. Okay, so that's problem number 11. Okay, we're starting here with number 12. So we're doing indefinite integral, which means that we have a function that we're going to end up with. Okay, so here we go. So this is the term in the parentheses, so we'll call that u. step number 1, choose u. Step number 2, calculate du. So the derivative of this expression is 3x squared plus 0. And then we multiply by dx. We look at original expression and we see we have, here's u, so we have, what we have left over is x squared dx. So what we're going to do is we're going to solve for x squared dx, and that's just going to be du divided by 3. So then we rewrite the original integral in terms of u. So x squared dx becomes du divided by 3, and in the numerator we have u to the 4th power. So if I plug u back in, I'll get u to the 4th, and then I take the derivative of u, and I get 3x squared dx, so I'd get 3x squared dx, 3's canceled out, and back to where we started. So now we have just a polynomial. What we'll do is we'll factor out the 1/3. And now if we go to page 250, we'll see that we can use the power rule formula. So what we do is we add 1 to the exponent, and we divide by the new exponent. We add our arbitrary constant c. So we integrated. We started with the function, which is function of x. We have used the substitution to rewrite the equation in terms of u. We've integrated in terms of u. And now we have the final answer, except that's in terms of u. And we want to go back to x. So all we have to do is look back to our original u value, or our expression for u, and u is equal to x cubed plus 5. So that's u. We raise that to the 5th power, divide by 15, and add our arbitrary constant c. And that is the answer. This is problem number 14. So we're asked to find the indefinite integral. Of this expression. And before I go any further, I'm going to open up my solution manual just to make sure I'm getting the answers correct, so I'm not misleading you. Okay, so I'm now ready to do that when I need to. Okay, what's in the parentheses? U. Calculate du. So we take the derivative of this with respect to x, and we'll get 8x. So this becomes 8x, this becomes 0, so we have 8x, and we multiply by dx. Now we're going to rewrite the original integral in terms of u. So we have x dx, so let's solve this previous equation for what we have. We get du divided by 8. And so now we can rewrite the original integral. So what we'll have is for x dx, we put in du divided by 8. And then the term in the parentheses is u. So I get u cubed over 8, factor out the 8. Okay, now it's a power rule, so we just integrate that. Integral of u cubed is we add 1 to the exponent and divide by the new exponent. So we'll get 1/32 u to the 4th, and I forgot my arbitrary constant c, got it carried away there. So I had c. So let's go ahead and put u back in. 4x squared plus 3 to the 4th power divided by 32 plus c. And that's correct. Okay, our next problem is 16. We have this integral of t cubed times square root of t to the 4th plus 5 dt. So a variable, independent variable is t in this case. Now before we start anything, let's rewrite the square root as a fractional exponent. So we get t to the fourth plus 5 to the 1/2 power. Okay, now we're going to use u substitution. So the u is usually what's in the parentheses. And we take the derivative, we get the differential du. The derivative of t to the fourth is 4t cubed, and then we multiply by dt. The 5 drops out because the derivative of a constant is 0. We go back to the original expression and see if we have 4t cubed dt outside the parentheses, but we have t cubed dt. So just like in the previous problem, we are going to divide by 4. And there's two ways of doing this. You could solve, so let me just show you the other way of doing it, is you could rewrite this as that du over 4 is equal to t cubed dt. So you can substitute for t cubed dt, you can put du over 4. So we'd end up with, let's just write it in here, you'd end up with t to the fourth plus 5 to the 1/2 power, and so we have t cubed dt. So the term in the parentheses is u, so we get u to the fourth. Actually, no, we get u is this, so we get u to the 1/2 times, instead of t cubed dt, we have du divided by 4. So then you can factor out the 1/4. So you get 1/4 the integral of u to the 1/2 du. I'm gonna do alternate this. We'll do some of them where we multiply and divide by the same number, and some that we solve for the what we do have. So this is the second way. Okay, so we integrate this, which we know how to do it. N is equal to 1/2, so n plus 1 is equal to 3/2. So we get 1/4. And the integral of u to 1/2 du is u to the 3/2 divided by 3/2 plus our arbitrary constant c. And we substitute back in, u is t to the fourth plus 5. And before we do that though, this dividing by 3/2 is the same as multiplying by 2/3. And so you get 2/12, which is 1/6. Okay, now I can stick it back in. So you get 1/6 times u, which we go over here, is t to the fourth plus 5 to the 3/2 plus c. And, that's probably as far as we need to go. You could say it's the square root of t to the fourth plus 5 quantity cubed. That's another way of writing the 3/2 power, but that one's probably good enough. (17) Integral of 5x times the cube root of 1 minus x squared dx. So we're going to put the variable x. We're going to do is rewrite this as a fractional exponent. So we have 5x. The cube's not on the x, it's the cube root. So we have 1 minus x squared to the 1/3 power dx. U is the term in the parentheses. 1 minus x squared. So we take the derivative of that. Du is going to be equal to negative 2x dx. So the derivative of negative x squared is negative 2x multiplied by dx. We go back to our original expression and say, what do we have here? We have 5x dx. Well, actually, let's factor out the 5. So we have 5x, 1 minus x squared to the 1/3 power dx. So actually what we have is x dx. So if we want x dx, we divide both sides by negative. Well, we're actually, this is the way we're doing it the original way. Okay. So what we need is negative 2x dx. So what we would do is we take 5, which is already here, times negative 1/2 times the integral of negative 2x times 1 minus x squared to the 1/3 power dx. I multiply by negative 1/2 and by negative 2, and you multiply those together and you get 1, which brings us back to this point. So then we say, okay, we have negative 2x dx. Negative 2x dx, so we can substitute for that as du, and this part we can substitute as u. So our constants in front we can go ahead and multiply out. Negative 5/2, the integral of u to the 1/3 power times du. This part, the red part's du. The green part here in parentheses, I didn't make it green, but this part here is that. So this becomes u to the 1/3 times du. Okay, now we just have a polynomial. So we add 1 to this. So we get u to the 4/3 power. 1 plus 1/3 is 4/3. How did we get that? 1/3 plus 4 plus 1, but that's 3/3. So 3 plus 1 is 4 with a common denominator, so you get 4/3. All divided by 4/3 plus c. So this becomes negative 5/2 times, well, we take the reciprocal of that and multiply it by. So by dividing by 4/3 is the same as dividing by the reciprocal of 4/3, which is 3/4. And let's see if we can simplify this. Well, not a whole lot. 15/8. And then finally we substitute u back in. U is equal to 1 minus x squared. So we get negative 15/8 1 minus x squared to the 4/3 power. And that's your final answer. Okay, we're up to 18, I guess. That's the next one. It's kind of odd because it has u's already, so I guess we'll have to use the different letter. So we get u squared times the square, what is this? Square root. U squared times the square root of u cubed plus 2 du. So we'll use w substitution because the variable is u. So we're going to let w equal u. Oh, we forgot to do one thing. I got to rewrite it as a fractional exponent first before we do that. So we get u squared times u cubed plus 2 to the 1/2 power du. Okay. Now w is the term in the parentheses. dw is 3u squared du. Again, this drops out, and this is just 3u to the 2 power times du. Okay, we're going to use the second approach now. We're going to look back, see what we have. We have u squared du. So to solve for u squared du, we're going to divide both sides. So we get dw over 3 is equal to u squared du. So now we can make that substitution here. So u squared du becomes dw divided by 3, and this is just w to the 1/2 power. Okay, so we can factor out the fraction. This is 1/3, the integral of w to the 1/2 power dw. it's a polynomial. So the integral of w to the 1/2 is w to the 3/2 divided by the new exponent, which is 3/2 plus our arbitrary constant c. Dividing by 3/2 is like multiplying by 2/3. So that's 2/9. And then we finally substitute w back in. So we get 2/9 u cubed plus 2 to the 3/2 plus our arbitrary constant c. Okay, now we're on problem 20. So we've been dealing with exponential cases. Now we're going to go to where the exponent is in the denominator. So problem number 20 has the integral of x cubed over 1 plus x to the 4th squared dx. So just like before, the u is going to be the term in the parentheses. And so du is the derivative of that. This goes to 0, and we get 4x cubed times dx. Since this is the fourth problem, we're going to use the procedure where we're going to multiply and divide by the same number. So what I'm going to do is I'm going to take this original integral. I'm going to multiply by 4, and I'm going to divide by 4. Before inside, before outside, but you can move constants across the integral sign. So we have 4x cubed dx in the numerator. In the denominator we have 1 plus x to the 4th squared. So we now make our substitutions, or use substitutions. So we have 1/4. The numerator is du. The denominator is u squared. So now we have to integrate that, which is just the same as, now this is where we rewrite things so that we move the exponent, term of the exponent to the numerator and change it to a negative sign. And then we can do the integration, because in this particular case, n is -2, so let's write that down. So people mess this up. N is -2, so n plus 1, that's what happens when we integrate, is -2 plus 1, which is -1. So the result of this integration is going to be 1/4 times u to the -1 divided by -1 plus c, which is the same as -1/4. Take the negative and put it there, and we can then move the u term to the denominator. And u to the first power is just u, so we get -1/4 times 1/u. And then finally we can substitute u back in, so we get -1/4 times 1 plus x to the 4th to the first power, or just by itself. We don't need to put the first power up there, plus our arbitrary constant c. So that is the correct answer. Okay, we're going to do 21. So 21 is x squared divided by 1 plus x cubed quantity squared dx. So u is the term in the parentheses. So we take du. Du is going to be, this is going to be 0, and the derivative of 3x cubed is 3x squared, and we multiply by dx. We look at the original equation, we see that we have x squared dx. So x squared dx is just du divided by 3. Divide both sides by 3. Then we can rewrite the original integral in terms of u. So the numerator, x squared dx, is equal to du divided by 3. And then we, in this case, we actually have 1/3. So 3 is in the denominator from this part. And then we have, in the denominator, we actually have u squared. Okay, factor out the 3 in the denominator is 1/3. And we'll rewrite u to the second power as u to the negative 2. 1 over u squared is the same as u to the negative 2 power. So now we, in this case, n is equal to negative 2, so n plus 1 is equal to negative 1. So we get 1/3 u to the minus 1 divided by negative 1 plus c. And that'll give us negative 1/3 u to the negative 1 power is 1 over u to the first power. And then finally we would substitute u back in. So we get negative 1 over 3 times 1 plus x cubed plus c. And that was problem 21. And the answer is negative 1 over 3, 1 plus x cubed plus c. Now we're on problem number 22. So I have the integral of x divided by square root. Actually, no, we're in 22. Actually, no, that's not right. X squared over 16 minus x cubed quantity squared dx. Okay, so this is our u. Turn the parentheses. 16 minus x cubed. Take the derivative, that goes to 0. We get negative 3x squared dx. So we get negative from there. 3 from the exponent. 2 becomes 1 less. So this time we're going to use the solution. We're going to solve for x squared dx from here. So what is x squared dx? X squared dx is equal to du divided by negative 3. So we just divide both sides by negative 3. So we can make that substitution here. Now we can just make a direct substitution. So this becomes du divided by negative 3. And then this term becomes u squared. Okay, well, we can factor out the negative 3 in the denominator. So we get negative 1/3 times the integral of du over u squared. And then we can rewrite it in this form so that we can integrate it. So we get negative 1/3 times u to the minus 2 power du. So again, n is equal to negative 2, n plus 1 is equal to negative 1. So when we integrate that, we get u to the negative 1 power divided by negative 1 plus our arbitrary constant c. Negative times a negative is a positive, so we get 1/3. And we can move that down to the denominator. So u to the minus 1 power is the same as 1 over u. C just is hanging around there. And then we can make the substitution back in. So u is equal to 16 minus x cubed. That's our answer. This is problem number 23. So we have the integral of x divided by the square root of 1 minus x squared dx. Okay, so u is term in parentheses or in terms in a rational radical. Okay, so I put 1 minus x squared, so du is equal to negative 2x, and then I add dx on the end. So the negative comes from there, the 2 is the exponent, you reduce the exponent by 1. You can see in our original expression here we have x dx. So to get x dx we divide by negative 2, so we'll get du, negative du over 2, so that's x dx. So we can rewrite the original integral. X dx is negative, so I'm going to write this as du's over here, and then I have a negative 2, and then I have the square root of u. So u is 1 minus x squared, so the square root of u. X dx is negative du over 2. So I'd factor out the negative 1/2. And this will become u to the negative 1/2 power du, because this is x to the u to the 1/2, and the denominator becomes u to the negative 1/2 in the numerator. So for integration purposes, n is negative 1/2. So when we add 1 to that, we get positive 1/2. So then we can just write it out. So we get 1/2 u to the positive 1/2 divided by 1/2. And we add our arbitrary constant c. So when we multiply the denominators together, you're multiplying these two numbers together. So 2 times 1/2 is 1. So this just simplifies down to u to the 1/2 plus c. And u is, we go back over here, we say, okay, that's 1 minus x squared to the 1/2 power. And this is the one instance where we actually go back and rewrite this as a square root. So 1 minus x squared plus c. So the integral, the original integral of this is that, the antiderivative. And that was problem number 23, so let me just check. Negative, oh, I missed a negative sign, didn't I? Where did I miss the negative sign? Oh, right there. So that's negative, that should be negative, that should be negative, that should be negative. Okay. Okay, let's see where we are. 24, 25. Okay, 25. I haven't done 25 yet. One plus 1 over t quantity cubed times 1 over t squared dt. Okay, we have two terms that are in parentheses, but this is the more complicated one because it has two parts to it. So I'm going to call u as 1 plus 1 over t. So du, well, before we do that, let's rewrite this as 1 plus t to the minus 1 power. So the derivative of 1 is 0. The derivative of t to the minus 1 is negative t to the minus 2. So you take the exponent, negative 1, and you decrease the exponent by 1. And then you multiply by dt, not du. And so that's the same as negative 1 over t squared dt. So what I have is 1 over t squared dt. So I need to solve for that. 1 over t squared dt is equal to negative du. So now I can rewrite the original integral as u cubed times negative du, which is the same as negative u cubed times du. So I just factored out the negative sign. So we have a polynomial. So we get u to the 4th, negative u to the 4th over 4 plus arbitrary constant c. And then finally we plug u back in, which was equal to 1 plus 1 over t raised to the 4th power plus c, and that's 25. So I get Oh, I forgot the fourth here, didn't I? So it's negative 1/4 times that. And that was number 25. So it's negative 1/4, 1 plus 1 to the 4th power plus c. Yeah, that's it. Okay, we're going to do number 29. So we have x squared plus 3x plus 7 divided by the square root of x times dx. And because it's in this section, you might initially be tempted to say, oh, it's u substitution, so don't be fooled. Because if we let u equal x, then nothing changes. And there's nothing in parentheses, so that's not going to help us. So what we have to do is just rewrite this by dividing each term here by the square root of x. So we'll end up with x to the 3/2 plus 3 times x to the 1/2 plus 7 times x to the minus 1/2 power, and everything times dx. So 2 minus 1/2 is 3/2. 1 minus 1/2, I'm talking about the exponents, x to the 1st power. And 7, this is the same thing as x to the 1/2 in the denominator. When you move to the numerator, you get that. So now they're all in the form of polynomials, so now we just add 1 to the exponent and divide by the new exponent. In this case, the second, we have 3, and then we integrate that, and we get x to the 3/2 divided by 3/2, and then we have 7 times x to the positive 1/2. Negative 1/2 plus 1 is positive 1/2 divided by 1/2. And we add our arbitrary constant c because we've integrated. So we take the reciprocal of 5/2, which is 2/5, and we have that. And then we take the reciprocal of 2/3, 3/2, which is 2/3. So we'll get 3 times 2/3, where those cancel out, and you get x to the 3/2. And then we have plus that. Okay, you take the reciprocal 1/2, which is 2. 2 times 7 is 14. X to the 1/2 plus c. And you may say, okay, I'm done. But what we could do is factor out a square root of x, so, or an x to the 1/2 power. And also, we have a 5 here, so let's factor out a 5. So what that leaves left, we have 2, and we have x squared. And then if you factor out a 5, you basically multiply each one of these by, if you factor out a 5, you multiply each one by 5. So this one, the 5's cancel out. Here you have 2 times 5, which is 10. And then you have x, because we're factoring out an x to the 1/2. So that'll leave with x to the 1. And then we add 14 at the end. And we add arbitrary constant c. And so x to the 1/2 is the square root of x. So we get the square root of x over 5 times 2x squared plus 10x plus 14. And then we add our arbitrary constant c. And let's see if that's what they do. Oh, they actually factor that a 2 as well. So I forgot to do one thing here. So I forgot to multiply this by 5 as well. So 5 times 14 is 70. So if you factor out a 2 as well, then you, since factoring out 2 in the numerator, you have to divide everything by 2, so you get this, and that would be the answer. Okay, let's see where we are. We're on 30. 30 is sort of like 26, but you may think there's more to it than there is. So we have t plus 2t squared divided by square root of t dt. So you think that's really complicated, but because we have this just one term in the denominator, we can actually break this up into two parts. And before we do that, let's rewrite the denominator as a fractional exponent. So we have t to the 1/2 power instead of the square root of t. So when we have t divided by t to the 1/2, that's t to the first power divided by t to the half. You subtract the exponents, 1 minus 1/2. So that leaves you with t to the 1/2. And the second one, we end up with 2 times t to the 3/2, because we have 2 as an exponent, 1/2 is an exponent in the denominator, so you take 2 minus 1/2 is 3/2. So really what we have is this. And at this point we can just use the power rule. So this term becomes, we add 1 to the exponents, so we get t to the 3/2 divided by 3/2. And the second term is the constant 2, t to the 5/2. 3/2 plus 1 is 5/2, and we divide by 5/2. And then we add our arbitrary constant c. And then we just clean it up. So that's the same as multiplying by 2/3. So we get 2/3 t to the 3/2 plus 2 times 2/5, reciprocal 5/2 2/5, times t to the 5/3 plus c. And so the final answer is 2/3 t to the 3/2 plus 4/5 t to the 5/3, 5/2, sorry. And actually we're going to see this in a second. Something that happens sort of like that. So this is kind of an introduction to something that we're going to see later. Okay, so that's problem 30. Okay, we're going to do a couple of trig ones right now. So let's do 44. So because the argument of the sign is not just x, then we would choose the argument of the trig function to be u. And when you take the derivative of that, you'll get 4x cubed dx. So with these two substitutions, we can rewrite the original integral. 4x cubed dx is equal to du. So we just put du on the end, and we end up with the sine of u. So we go to page 250 and we say, okay, do we have a trig function? Can we integrate that? And the answer is yes. The integral of the sine is negative the cosine. We add our arbitrary constant c, and then we substitute back in. U was equal to x to the 4th. So that is the integral, and that was number 44. So let me just check. That's correct. And we don't need to include these parentheses in the final answer. We can just say it's cosine of x to the 4th. Now remember, the difference here is if you had the cosine of x, the whole thing to the 4th power, that's written shorthand as cosine to the 4th of x. But when the power is here and there's no parentheses, then we assume it goes with the argument. Okay, so we're going to do a couple of trig problems now. So 45, pretty easy. We have the integral of the sine of 2x dx. So we don't show it, but the argument in the sine function is 2x. So we're going to let u equal 2x. Therefore, the derivative of 2x is just 2. Derivative of 2x is 2, and we multiply it by dx. Let's solve for dx. dx is equal to du over 2. So for dx, we can put du over 2. So we have the sine of 2x, but 2x is u, so we get the sine of u times dx, which is du over 2. And we can factor out the half to the denominator. So to get the integral of the sine of u du. Okay, we know what the integral of that is. The integral of the sine is negative the cosine. Go to page 250. add our arbitrary constant c, and then we substitute back in. So we get negative 1/2. I'm just taking the negative and included with the constant cosine of u, but u is 2x plus c. So that's my final answer. Again, if I take the derivative of this goes to 0. The chain rule says the cosine of 2x is 2 times, it's going to be cos 2 times negative the sine of x, because the derivative of the cosine is sine, so you get negative the sine of 2x. The negatives cancel out, the 2 cancels out with the half, and you're back to where you started from. Okay, let's see what's next. 45, 46, let's do 46. And so 46 is the integral of the cosine of 6x dx. So again, the argument of the cosine function is not just x, so we're going to choose that as u. So we take the derivative and we get just 6. The derivative of 6x is 6, and we add the dx. So we look back at our original expression, we've got just dx, so we solve for that. So dx is du divided by 6. So now we can rewrite the original expression. We'll have the cosine of u times dx, which is du divided by 6. So we can factor out the negative, the 1/6. So we get the integral 1/6 times the integral of the cosine of u du. And the integral of the cosine is, if you go to page 250 and look at the formula, it's the sine. And then we add arbitrary constant because we're doing an indefinite integral. And then finally we plug in what u is equal to, which is right there, 6x. And so that is the answer. This is problem 48. So we have the integral of x, sine of x squared dx. The argument of the trig function is not just x, so we're going to call that u. The derivative of u is going to be 2x, and we multiply by dx. We go back to the original equation, and we see that we have just x times dx. So there's no constant, so we solve for x dx, and it's du divided by 2. So with this substitution, the expression can be written as the sine of u, sine of x squared, which is u, and we divide by 2 from here, and we multiply by du at the end. Okay, factor out a half. The integral of the sine is the cosine, or negative the cosine, so we get 1/2 negative the cosine of u plus arbitrary constant c. So we get negative 1/2 cosine of u. U is x squared from here. And so the final answer is negative 1/2 cosine of x squared plus c. Okay, so that's right. 49. The integral of the sine of x, actually the sine of 2x, cosine of 2x, dx. So you might think that u is 2x, but that's not the case. That was the case in the previous problem. In this case, we could either choose u as being the cosine or the sine. It doesn't really matter. So I'm going to choose, let's actually do it both ways just to show you that it doesn't make any difference. Why doesn't it make any difference? Okay, so if we let u equal the sine of 2x du, well, you have to use the chain rule here. The derivative of the sine of 2x is going to be equal to 2 times the cosine of 2x, and then we add the dx term. Okay, so you see that we have cosine of 2x dx here, and we have it there. So again, let's do the substitution. So if you solve for the cosine of 2x dx, it's going to be equal to du over 2, divided both sides by 2. So if I make that substitution, if I make those two substitutions, this for u and this for cosine of x dx, you end up with u times du over 2. Factor out the 2 in the denominator, so we get the integral of u du. So the previous problem we had the sine of u du. In this case we just had the polynomial. It's just to the first power, so when you integrate that you get 1/2 the constant. You get u squared, add 1 to the exponent, you divide by 2. Plus arbitrary constant c. So, and then you multiply 1/2 times 1/2, so you get 1/4 u squared plus c, and then you plug u back in, and we get 1/4 times the sine of 2x quantity squared plus c, and that's the same as 1/4 the sine squared of 2x plus c. So you rewrite this either as the quantity squared, you can put the square there. It means the same thing. So that's one answer. Now the second answer is, what if I let u equal cosine of 2x? So let's do that. So we're going to let u equal the cosine of 2x. The derivative of that, well, the derivative of the cosine is negative sine. So we get negative, and we have the 2 from the inside, so you get negative 2 sine of x and sine of 2x. So remember, the argument doesn't change. So we get negative 2 sine of 2x dx. So it looks very similar. We can solve for the sine of x dx, or the sine of 2x dx. Sine of 2x dx is just equal to negative du over 2, because we divide by negative 2. Instead of here we had d over 2, here we have negative d over 2. So the original integral, this is actually u, and then we have times negative du over 2. So we can factor out the negative 1/2 in the denominator, and we get the integral of u du. Just like before, we're going to have, we have negative 1/2 instead of positive 1/2. We have u squared over 2 plus c. So we get negative 1/4 u squared plus c. But in this case, u is not sine of 2x, but it's cosine of 2x. So we get negative 1/4 cosine of 2x quantity squared plus c, which is negative 1/4 cos. So we can put the squared here, just cosine squared of 2x plus c. So here I get 1/4 sine squared of 2x plus c. Here I get negative 1/4 cosine squared of 2x plus c. But the way we link these two is the Pythagorean identity, which says the sine squared of x plus the cosine squared of x is equal to 1. Or we could say the sine squared of 2x plus the cosine squared of 2x, it doesn't matter what the argument is equal to 1. So here, for we can solve for the cosine squared of 2x is equal to 1 minus sine squared of 2x. So if I make that substitution here, you can see what I'm going to get. Let me add a page. So if I make that substitution here, I'll get negative 1/4 times 1 minus sine squared of 2x plus c. And when I multiply these, then I get negative 1/4 plus sine squared of 2x plus c. You say, well, that's still not exactly the same, because I had 1/4 sine of 2x, back down here. 1/4 sine squared of 2x plus c. Here I have c plus 1/4 or minus 1/4 or something. But the thing is, this is a completely arbitrary constant, so what I do is I combine these two together and just call that C, because this is a constant, this is some other constant which is completely arbitrary. So I can replace this and say it's sine squared of 2x plus this arbitrary constant C, which are determined by the initial conditions, or they drop out if it's a definite integral. So that's how we get the same result. So it doesn't matter which way we do it, we get the same answer. So this is problem 50, which is very similar to what we just did. It's just a different trig function arrangement, but we have the integral of secant of 1 minus x times tangent of 1 minus x times dx. In this case, we do actually want to choose, well, in this case, there is an integral of the secant tangent, so we let u equal 1 minus x. So du is equal to negative 1 from this times dx, or dx is equal to negative du. So we can make the substitution, and we get the secant of u tangent of u times negative du, which means we can factor out the negative sign, put it up front. If you go to page 250, you'll find that the integral of the secant tangent is the secant. Let me just check that for sure. I'm pretty sure that's what it is. And secant tangent is secant. So we know this integral is secant of u plus arbitrary constant c. Then we make the substitution back in, so we get secant of u, but u is 1 minus x. That's our answer. Okay, we do 51. Integral of the tangent to the fourth of x secant squared x dx. So because we just have x in here, that means that we're probably going to want to choose either the tangent of x, so u is either going to be the tangent of x, or u is going to be equal to the secant of x. And so we take the derivative of each one. The derivative of the tangent is the secant squared of x times dx, and the derivative of the secant is the secant x times the tangent of x, and we multiply by dx. So if we were to let u equal this, we'd have u to the fourth, and this would be du. So that one works out. As far as this one is concerned, if we let secant equal u, then you'd get, this would be u squared, and you'd have tangent left. Well, I've got tangent and secant. So let's say if we just let one of the secants, we take the derivative of the secant, you'll have secant tangent, but I've got secant tangent to the fourth. So that one is not going to work under any circumstances. So it's the first choice. And since we have exactly what we need here, we can rewrite the original expression as u to the fourth, tangent to the fourth, times secant squared dx, which is du. So when you integrate that, you'll get u to the fifth, add 1 to the exponent, divide by the new exponent 5, and you add your arbitrary constant. And now you just plug back in. So you get tangent of x to the fifth divided by 5 plus your arbitrary constant. And you could rewrite that as in this shorter version. So that was problem number 51. Okay, let's do 52. So we have the integral of the square root of the tangent of x times the secant squared of x dx. Again, either tangent or secant could be u, but as in the previous cases we've had, we let u equal
Well, there's two reasons, because we have it under the square root, so that's more likely. And the derivative of the tangent is the secant squared, so we see the secant squared there, so that works out perfectly. So this part's du, this part is u, so we get the integral of the square root of u du as our substitution using u defined as such and du calculated as such. So that's equal to the integral of u to the 1/2 power du. It's a polynomial, so you add 1 to the exponent and divide by the new exponent. We have arbitrary constant c because we're dealing with indefinite integrals, and so we'll take the reciprocal of 3/2. So we multiply by 2/3, and that's going to be multiplied by u, which is the tangent of x, and we're going to raise that to the 3/2 power and add our arbitrary constant c. And that's 52, 2/3 x to the 3/2, yeah, tangent x, so that's correct. 53. So we have the cosecant squared of x divided by the cotangent cubed of x, and the whole thing times dx. So it looks pretty complicated. But again, we look at the derivative of the cotangent and the derivative of the cosecant. And so you go to page 250, and I don't remember it exactly, so I'm going to look. Page 250 is our list of known derivatives. So we're looking at derivatives, because when you do the u, and I'm going to choose u as the cotangent. That will be the correct choice, okay? And I'll show you why here. So the cotangent of x is u. So you look on page 250 in the left column, and you see what's the derivative of the cotangent? Well, it's negative the cosecant of cosecant squared of x. And we add the dx to the end. So you can see we have cosecant of x dx. So we can solve for that. Cosecant squared of x dx is equal to negative du. So we just multiply both sides by -1 to solve for cosecant squared of x dx. So now we can make the substitution. So the numerator becomes du. And then we have 1 divided by the cotangent. Cotangent is u, so we have 1 over u cubed. So that's our expression, which we then rewrite as u to the -3 power du. We integrate by adding 1 to the exponent, dividing by the new exponent, and adding arbitrary constant c. So that's the same as -1 over 2 u, but u is equal to the cotangent of x, and we square that. So here -2, but it becomes +2 when you put it in the denominator. And then again, we can finally put it in its shortened form, so we can write it as, not u, but x. The reason we knew to try one of the trig functions instead of the argument of the trig function is it's just x by itself. So that's number 53. And okay, interesting. Okay, here's a little additional thing that you could do. And it's, I forgot my arbitrary constant c here. So this little trig identity stuff. So we could say that's negative the tangent squared of x over 2. Plus c, because the cotangent is 1 over the tangent, or the tangent is one over the cotangent of the tangent. So we get that, and then what you could do is you could use one of the Pythagorean identities. So if we remember, one of the Pythagorean identities is the one that I remember is this. So if you divide each one by the cosine, and the reason why I choose the cosine is because I want to get the tangent in that first term. So you divide each term by the cosine. You get tangent squared of x plus 1 is equal to 1 over the cosine is the secant, so you get secant squared of x. So that's the other trig, Pythagorean identity. So what we could do is we could substitute in for, if you solve for tangent squared of x is equal to secant squared of x minus 1. And I'm just thinking here for a second. Okay. So we plug that up in there, you'll get negative the quantity secant squared of x minus 1 divided by 2 plus c. And so then you'll get negative secant squared of x divided by 2 plus 1/2 plus c. Well, you can combine these two and just call it c, because this arbitrary constant is defined by some initial conditions which we haven't set yet. So we can just, anything that's left over is constant, so we can put into, lump it in. And so you end up with, I'm worried about my negative sign here. Let's see, did I get a negative sign screwed up somewhere? I'm just looking at this, their answer. I think I did. Let me go back. Negative. Yeah, I forgot. I just forgot negative du right there, didn't I? So that's negative. That's negative. That becomes positive. 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 So this is positive. That's positive. That'll turn to negative. But the same thing applies. So you end up with secant squared of x over 2 plus some arbitrary constant. So that's one way of looking at it. The other way of looking at it was this original one right here. What's the advantage? Not a whole lot. The only thing is here is if you, well, actually this probably would be the easiest one to use the calculator for, because you've got tangents. You don't have secant or cotangent, so this might actually be the best solution. Okay, the next group, okay, we have this special kind, 65 and 68 are a special kind of integral. So in this case, 65, we have x squared times the square root of 1 minus x dx. So you might think, oh, well, this is u because it's on the square root, but if you take the derivative of that, you don't get x squared. So what we do is we let u still equal what's in the parentheses. And du is found the same way. We get negative 1 times dx. But then what we do is we use this first equation to solve for x. So x is equal to 1 minus u. So if you add x to both sides and subtract u from both sides, you'll get this. So we make 2 substitutions. 3 substitutions, actually. You can see that dx is equal to negative du if we multiply both sides by negative 1. So what this integral becomes is 1 minus u squared. So that x is 1 minus u, and we square it. And then we multiply it by 1 minus x, square root of 1 minus x, which is u to the 1/2 power. And then we multiply it by dx, which is negative du. So now we've got this whole thing in terms of u. We can factor out a negative sign from here. So we get 1 minus u squared u to the 1/2 du. And typically you have to just multiply everything out and then integrate it. You can't really use a chain rule or anything like that. So this term here becomes 1 minus 2u plus u squared, just by using FOIL. You get 1 squared, you get negative u times 1 twice, so you get negative 2u, and then you get u squared. It's negative times negative, so you get positive. Then you multiply by u to the 1/2 du. Now you distribute this to each term, so we get u to the 1/2
minus 2u to the 3/2. That's because we're into the first power. So 1 plus 1/2 is 3/2. Plus u to the 5/2. Because we have 2, which is 4/2, plus 1/2 is 5/2. Whole thing times du. And I just integrate each one of these using the power rule. So we get negative, and you get u to the 3/2 divided by 3/2 minus 2 times u to the 5/2 divided by 5/2. These, I'm adding 1 to each one of those as I integrate. U to the 7/2. 5/2 plus 1, 2/2 is 7/2. So I just done that, and I add my arbitrary constant c. So each one of these I'm going to take the reciprocal of. I'm going to multiply it by negative sign. So we get negative 2/3 u to the 3/2 plus 2 times 2/5 u to the 5/2 minus 2/7 u to the 7/2, all plus my arbitrary constant c. Now I could substitute in u right now, use 1 minus x squared, but one thing you can do is you can factor out u to the 3/2. And what that will leave is negative 2/3 times 1. That's all 2/3. When you factor out 3/2 from 5/2, you just left u, so we get plus 4/5 u minus 2/7 u squared. Because if you factor out 3/2, you're left with 4/2, which is 2. And now we can substitute u in. So we get 1 minus x to the 3/2 times negative 2/3 plus 4/5 times u, which is 1 minus x minus 2/7 times 1 minus x squared plus c. You could actually multiply all this stuff out and combine like terms, but I think that's good enough. So again, what we do is when we have this case where it doesn't fit, and in a test I'll say use this is a different kind. This is the second kind, so you'll know to do this. You let u equal what's in parentheses of square root. It's usually a square root term. You take the derivative, get du, so that you can make the substitution here. And then you solve this equation for x so that you can substitute that in there. So you make all those substitutions. You multiply out any terms that are squared. So what I did there was I squared everything. 1 minus u, 1u squared ended up being this. And I distributed this term to each one of those 3, and I got these 3 terms. Then I integrated them. They're polynomials. So this half becomes 3/2, 3/2 becomes 5/2, 5/2 becomes 7/2. And you divide by the corresponding new exponents.
Okay, this is an example of another one of those second kind of u substitutions that requires the one additional step. So normally you might instinctively think that u is equal to 2 minus x, which is correct, but if you did du, you would not get this times that, so we have to go one more step. So remember, we still determine the radical sign there. So you take du, and what you get is a negative dx. So that's du. So dx, if we solve for dx, is what we have there is negative du. Just multiply both sides by -1. Now the additional thing we have to do is solve for x. So if we solve for x, you'll get x is equal to 2 minus u. If I move this to the left-hand side, it becomes positive. Move this to the right-hand side, it becomes negative. So you get 2 minus u. So then you can make the substitution. So we have the quantity x. X is 2 minus u. And then we add 1. And then we have the square root of u, all times negative du, because dx is negative du. So let's clean that up a little bit. 2 plus 1 is 3, so we get 3 minus u times, and we have a negative sign, so we put that, well, let's take the negative sign and just change, so it becomes u minus 3 instead of 3 minus u. So this negative sign is going to be multiplied by 3 minus u, becomes u minus 3. And then finally you have to multiply it out, so you always end up with fractional exponents in these problems. So now we have this polynomial, so you just add 1 to the exponent. So 3 halves plus 2 halves is 5 halves. We divide by the new exponent. The second one, we have the constant 3. We take u to the 3 halves and we divide by the new exponent, which is 3 halves. And we add our arbitrary constant c to the whole thing. Okay, take the reciprocal, so you get 2/5 u to the 5 halves minus, okay, so you take the reciprocal, you get 2/3. 3 times 2/3 is 2, so just have 2 u to the 3 halves plus c. And then we can substitute back in. Remember, u, what was u equal to? 2 minus, u is equal to 2 minus x. So you could plug that in there now. So let me just do that. That'd be one way. 2 minus x to the 5 halves minus 2 times 2 minus x to the 3 halves plus c. Okay, so now what do I do? Well, I could factor out something, but I'm going to do the factoring, so that'd be one solution, and I'd be happy with that. So, and you can't move this inside because it's to the 3 halves power, so you have to do some weird things to get that. So you leave these constants out front. Don't try to get too fancy. Okay, up here, if we factored out u to the 3 halves and also 5, what that would leave is 2u. Okay, 3 halves minus 5 halves minus 3 halves is 1. So you'd have u to the first power. And the 5, so to factor out of 5 means multiply everything by 5 and then doing that. So I take 5 in the denominator, I have to multiply by 5 in the numerator. And anyway, so you get 2u, and here we would get negative 10 because there is no denominator, so we're just multiplying 2 times 5 is 10. And we've already factored out u to the 3 halves. I'm just going to leave an arbitrary constant out there. So now we would plug u back in. So you'd get 2 minus x to the 3 halves divided by 5 times 2 times u, which is 2 minus x minus 10 plus c. And then we would just simplify what's in the second parentheses. So what would we have? Well, we'd have 2 times 2 is 4. Then you have a negative 10, so positive 4 minus 10 is negative 6. So actually I'm going to factor out a negative sign, so we'll have, because what's going to happen is I'm going to have 2 times negative x, which is negative 2x, but if I factor out the negative sign, I'll get 2x. And here I had negative 6, which become positive 6 by factoring that out. And so that was problem number 66. So there, oh, and you could factor in another 2. Okay, so I have one more step. So there's a common factor of 2. So if I factor that, I'll get 2/5, negative 2/5 times 2 minus x to the 3 halves times x plus 3. Let's see if that's what I have. Negative 2/5, 2 minus x to the 3 halves, x plus 3 plus c.
Okay. So we're going to do problem 68, which is another one of these kinds of problems that we use different U substitution for. So I have the indefinite integral of 2x plus 1 divided by the square root of x plus 4 dx. So what happens? Well, again, if you took this as being u, x plus 4, the derivative of that would be 1, so it doesn't match up with that at all. So we are still going to use the u substitution, x plus 4. So when you take the derivative, du is just dx. We can solve for x. So x is equal to u minus 4. So I subtract 4 from both sides. So then I go back up here and I make those substitutions. So we have 2 times u minus 4 plus 1 divided by the square root of u times du. So for dx we put in du. For x plus 4 we put in u, and for x we put in u minus 4. So let us, we'll have 2u minus 8 plus 1 divided by the square root of u. And then we can simplify the numerator. It's going to be 2u minus 7 divided by the square root of u. Now, at this point, we can just create two separate fractions. And actually, before we do that, let's rewrite the square root of u as a fractional exponent. And now we can do it. So this is u to the first power. So when you have u to the first power divided by u to the minus u to the half power, the result is u to the half power. So we get 2 times u to the 1/2 power from this fraction. Our second integral is going to be negative the quantity 7 divided by u to the 1/2 power. So we have the half power in the denominator and the second part half power in the numerator. So now these are just power rules. So we have 2 the constant times the integral of u to the 1/2, which is u to the 3/2, divided by the new exponent, which is 3/2, minus 7 times the integral of 1 over u to the 1/2. Well, that's, again, this part here is going to be 7 times u to the minus 1/2 power du. So we take this positive exponent, move it to the numerator, make it negative. So when we add 1 here, we get u to the 1/2, because it was negative 1/2. Negative 1/2 plus 1 is positive 1/2. And we divide by the new exponent, which is a half, and then we add our arbitrary constant c. We're going to clean this up a little bit before we substitute back in. So we'll have 2 times 2/3 instead of 2 divided by 3/2. So multiplying by the reciprocal is the same as dividing by something. So the reciprocal of 3/2 is 2/3. And we have 7 times the reciprocal of 1/2 would be 2. 2 over 1. 1 over 2 is the reciprocal of 2 over 1. So that becomes 4/3 u to the 2/3, 3/2, pardon, minus 14 times u to the 1/2 power. We're going to do one more step here. We're going to factor out u to the 1/2 power. And that'll leave us with 4/3 u minus 14. So if you see I multiply this back out, I'll get 4/3 u to 3/2 minus 14 u to the 1/2, which is the same as we have there. So what is u? U is equal to, go back to the beginning, u is equal to x plus 4. So that's the substitution we have. U plus x plus 4 substituted, x plus 4 to the 1/2 power times 4/3 times x plus 4 minus 14 plus c. And we can simplify this by multiplying this out. So what we'll have is x plus 4 to the 1/2, and we get 4/3 x plus 16/3 minus 14. And we can combine these two terms, and we'll change this into a square root. So we'll get the square root of x plus 4 times 4/3 x. And remember, 14 would be the same as 14 times 3 divided by 3, which is 42/3. So if we take 16 and subtract 42, we get 26. So where goes 14? So 42 minus 16. So 12 minus 6 is 6, bar 1. So we'll have 3 minus 1 is 2, so it's 26. So we have 26 thirds plus c. And we could also, if we could factor out a third, so we'd have the square root of x plus 4 divided by 3 times 4x minus 26 plus c. Okay, let me just check the answer here. Okay, so that's basically the right solution. What they did is they factored another 2 out, so you'd have 2 thirds times the square root of x plus 4 times 2x minus 13. Why would we do that? Well, it's just you have a common term here. You have a common factor of 2, so you could make this a little bit smaller, but in general, it's pretty much the right answer. Okay, we're on to 71 now. It says evaluate the definite integral. So that's the difference. This is their definite integral. So it's really not a whole lot different, except we'll get a number instead of an equation. So we have the integral from 1 to negative 1 to 1 of x times x squared plus 1 quantity cubed dx. So we're just using u substitution. There's actually 2 ways to do this. You can redefine the limits in terms of u, or you can just substitute back in. So let me do it both ways. So we let u equal the term in the parentheses, x squared plus 1. So we take the derivative, and we get 2x from here, nothing from there, and we multiply it by dx. So let's solve for x dx. What is x dx? Well, all you have to do is divide both sides by 2, so we get x dx is equal to du over 2. Okay, now we can make the substitution. I'm going to leave the limits. The limits are actually in terms of x. But as long as we don't substitute in until we make the actual final, once we get the thing back in terms of x, then we can do the substitution. If not, we'll show you what we do. So x dx becomes du over 2. The term in the parentheses is u, so we get u cubed times du over 2, which is the same as, you can factor out the 2 in the denominator is a half. So we have the integral of u cubed du. So now we integrate with respect to u. So we have a constant still. We get u to the 4th, so adding 1 to that exponent, dividing by the new exponent 4. And we're going to evaluate that between negative 1 and 1. But that's in terms of x, not in terms of u. So what we would get is, let's before we do that, let's just make it 1/8. So 1/2 times 1/4 is 1/8. U to the 4th between negative 1, positive 1. Okay, now we have to substitute back in u, so it would become negative 1/8 times u, which is x squared plus 1 evaluated between x equals negative 1 and x equals positive 1. So now we can make the substitution of the limits. So we get 1/8. The upper limit is x squared. So we have x, we're going to do the upper limit first. So we have 1 squared plus 1. And then we subtract it at the lower limit, which is negative 1 squared plus 1. So that's from here and here. So 1 squared is 1, plus 1 is 2. And then we subtract off 1 squared is, negative 1 squared is also positive 1, plus 1 is 2. And so you can see what happens. These cancel each other out. You actually get 0. What we'll find is that this is a symmetric equation, and that I forgot something here. I just realized something was going on here. So this is the 4th power. I forgot that part. So this is the 4th power, and this is the 4th power. So, yes, okay. So it does go to 0. Now we'll look at it graphically here in a second. So this is still 2 to the 4th power. This is 2 to the 4th power, and they still cancel out. You still get 0. Okay, I forgot the 4 when I went from here to here. Okay, so what it's saying basically is it's saying it's symmetric about the origin, but one part's above the axis and one part's below the axis. So let's just use a graphing utility to verify our results. So we're going to open up a graphing utility, the usual one we use. So what we're going to do is we're going to put an equation. The equation was x times x squared plus 1 quantity cubed. So we have x times x squared plus 1 quantity cubed. So that's the function. And we're going from negative 1 to positive 1. So let's make it from negative 2 to positive 2 so we see at least most of this thing. So here it is. So that's what the function looks like. And we went from negative 1, so let's zoom out a little bit in the y direction so we can see where it intersects. So the area that we're actually looking at is, we take, this is your lower limit, x equals negative 1. This is your upper limit, x equals positive 1. So this is actually going to give us a negative number, and the area here between this red curve and the x-axis is positive. So since they're symmetric, this value is equal to that value in terms of magnitude, and then they cancel each other out because one's plus and one's minus. So that's the basic idea. Now sometimes graphing utilities will let you do integration. So let's see if it does. There's one here that says integral. Function to be integrated. So the function to be integrated is x times x squared plus 1. Our lower limit is negative 1. And we want to calculate the absolute integral, I think. Let's make the minimum be negative 2 and the x max be 2. So let's make x min be 8, or actually, yeah, let's get negative 8 and positive 8. Okay, so what we have, let's see if what this is showing is, I'm going to change the view so it's not in terms of pi. So this is the function. We're starting at the lower limit is negative 1. So here's our area below the curve. Here's the area above the curve, and then we're asked to find the area. Well, I think that we don't do absolute integral. There we go. So this is actually the area underneath the curve as we go along. So you start out with 0 area, and then as you go along you get more area, and the area is increasing, but then it increases very little right here. So we get the maximum negative area here, and then we do the same thing. We have this area up to 1 is positive, so the total area ends up coming back to 0 here. So that's the actual integral. This curve here, the red curve, represents the integral from -1 to some value of x of the function x times x squared plus 1 cubed dx. So if you plug x equals 1 in here, you're basically looking right here, and so it's saying the red curve is the integral. So it's saying the integral from -1 to 1 of x times x squared plus 1 cubed dx is 0. It also says that if we integrated from -1 to 0 of that function, we would get something like -0.8 or 7 or something like that. So that's this area. And then if we had this area and everything we had was negative here gets canceled out by positive here, and you come out to 0. And if you keep going, then the area keeps getting bigger and bigger positive because you have this big area. So actually we'll do integration if you understand what the curve's telling you. Okay, so let's go back here. Stop sharing. Start sharing. Okay, so that was why we got 0 when we integrated from -1 to 1.
Okay, we're going to do 72. So now we're going to do some definite integrals. So that means we're finding area. Definite integrals mean area. It means a number, not an equation. Okay, so that's squared. So our u would be determined in the parentheses, and du would be the derivative, which would be 3x squared dx. In the original expression, we have x squared dx, so that's what we need for our substitution. So that's going to be du divided by 3, divide both sides by 3. Now we're going to also do redefine the limits. So when x equals 2, u is equal to -2 cubed plus 8. -2 cubed is -8, so it becomes 0. And when x equals 4, u is equal to 4 cubed plus 8. 4 cubed is 4 times 4 is 16 times 4 is 64. So you get 64 plus 8 is 72. So we can rewrite the original integral. We can change the limits from 0 to 72, and we'll have u squared, because that's u squared. X squared dx is du over 3, so we'll divide by 3 and multiply by du. So when we integrate, so that's also equal to 1/3 integral from 0 to 72 of u squared du. So we know that's a power function. So we get 1/3 u to the 3rd power by adding 1 to the exponent, dividing by the new exponent. And so that gives us u cubed, and let's not get going too fast here. So that's going to be evaluated between u equals 0 and u equals 72. So we get u cubed over 9, multiplying the 2 3's in the denominator, and you can see that when we plug 0 in at the lower limit, it's going to go to 0. So the answer is just 72 cubed over 9. 72 cubed, that's a big number. Hopefully I did this right. Yeah, it's a big number. Okay. So 72 to the 3rd power divided by 9. So we get 41,472. And that is what the answer is in the book, so it must be right. Not always true, but that.
Okay, so we're going to do 74. 74 is just the normal integral. So we have the integral from 0 to 1 of x times the square root of 1 minus x squared dx. So our choice for u is easy. It's 1 minus x squared. And hopefully du works out. So the derivative of this is negative from here, negative 2 from the exponent. Raise x to the 1 power, which is just that, and we multiply by dx. So in the original equation, you see we have x times dx, x dx. So we can solve for that here. X dx is equal to du divided by negative 2. So this part here is just these two terms. And this part here is the term in the parentheses. So when I make those two substitutions, we'll get something. But let's go ahead and change the limits while we're at it. So at x equals 0, which is the lower limit, we get 1 minus 0 squared, which is 1. At x equals the upper limit, we get u is equal to 1 minus 1 squared, which is 1 minus 1, which is 0. So we can rewrite the original integral, which is in terms of x. We're going to substitute the lower limit with 1 instead of 0, and we're going to make the upper limit 0. And that's fine. We can do that. It doesn't matter what order the limits are in. Just be consistent. X dx becomes du over negative 2. And here we get the square root of u. So 1 minus x squared is u, so we get the square root of u. Let's factor out this denominator. So we'll get negative 1/2. The integral from 1 to 0 of the square root of u, which is u to the 1/2, times what's left here is du. So this is just a polynomial. So we get negative 1/2. The integral of u to the 1/2 is u to the 3/2 by adding 1 to the exponent and divide by the new exponent. And then we evaluate that between our lower limit, which is 1, and our upper limit, which is 0. Okay, before we do the evaluation, let's clean this up. So we have negative 1/2 times the reciprocal of 3/2, which is 2/3, times u to the 3/2 between 1 and 0. 2's cancel out, so we get negative 1/3 u. We're going to use u is 0 at the upper limit, minus 1, which is the lower limit, also to the 3/2 power. So this is this function evaluated at 0 minus it evaluated at 1. So we get negative 1/3 times basically negative 1, because this is 0. And this 1 to the 2/3 is 1. 1 to any power is 1. And so you get negative 1/3 times positive negative 1 becomes positive 1/3. And so that's the answer. That's the area underneath this curve between 0 and 1. So we're going to draw the graph, and then we'll do this integration thing. So let me let's stop sharing it there. Start sharing it. Here's the graph function. So what we're going to put is the original equation that we want to integrate, which is equal to x times the square root of 1 minus x squared. And let's plot that between 0 and 1. And I don't know what the values of x, y are going to be, so we'll just plot it and see what happens. Okay, so here it is. This is what it looks like. We'll zoom in the vertical direction. So we go to here and push the zoom button. So what we're doing is we're looking for the area underneath this curve between 0 and 1. So it's going to be positive because everything's above the curve. And let's just think about what we have here. If we wanted to kind of guesstimate, well, the width is 1. So, what's the average height of this thing? Well, if you took just the average of these two, the 0 and that, you'd end up with 0.25. Half of 0.5 is 0.25. And 0.25 times 1 is 0.25, so that would be one estimate. But it turns out that, and that would be true if this were straight, but it has this curve, and this curve makes it so there's more up here than down there. So it's going to be a little bit more than 0.25. So that, the area given by the solution is 1/3. So we're saying that if you took 1/3 and you drew a straight line across here, height of 1/3 times width of 1 would give you the total area. That'd be your average value, would be 1/3. And basically what we're saying is that the stuff below the curve is the same as the stuff above the curve. So let me just draw it in here. So it's going to be right close to here. So I'm just going to put some dashed lines in, or dots. It's hard to draw straight lines. So that would be your average value. The integral divided by the b minus a, which b minus a is just 1 in this case. So what we're saying is that this area, which is above the red curve, below the green, and this area here is going to be equal to this area, which looks about right. So the area between here and there is the same as the area between there and here. It all balances out so that we get an average value around 0.3. Okay, now let's look at the integral. So let's go to the integral. So our function is x times the square root of 1 minus x squared. We're going to go from a minimum of 0 to a maximum of 1. And the area is going to be, we're going to go from 0 to 0.5, because we know the total area is 1/3. So if we integrate that, we get, so that's the function. Now, where's the integral? X times the square root of 1 minus x squared. Oh, we must have not changed the lower limit. Oh, wait. Oh, we have to change that to 0. So the lower limit is 0. That's what happened. So I'm going to change this again. So x min is 0. X max is 1. Y min is 0. X max is, well, we need it to at least 0.5 because that's where it goes to. So we're going to put 0.5. 0.5. So that's the maximum the function gets. Integrate from 0. So there it is. The blue curve is the function. The blue hash is the area that we're representing. And of course there's 0 area here because there's no width. And as we go along here, we get more and more area. We're putting the most area on right here, and then we start to decrease it. We're still adding area, but we're adding it at a lower rate. So if you see, this corresponds to that point. This is like a point of inflection. Oops, don't do that. Okay, let me change the limits here so we can see. So I go from 0 to 1, 0 to 0.5. That's where before integrate. Okay, so you can see this is the value of the integral from 0 to 1, and it's 0.33, which is what we calculated, 1/3. If our integral went from 0 to 0.7, we'd have this as our area. If it went from 0 to 0.4, that would be our area. So again, what the red curve is showing is the integral from 0 to x of x times the square root of 1 minus x squared dx. When x equals 1, then we get that particular value, which turns out to be 1/3. This is number 75.
So we have the integral from 0 to 4 of 1 divided by the square root of 2x plus 1 dx. So u is going to be what's in the radical sign. So we get 2x plus 1. So du just is 2. Derivative of that expression is just 2 and multiplied by dx. What we have in the original expression is dx. So let's solve for dx. Dx is du divided by 2. We're also going to redefine the limits. So when x equals 0, u is equal to 1. 2 times 0 plus 1. When x is equal to 4, u is equal to 2 times 4 plus 1, which is 9. So our old limits were from 0 to 4. Our new limits are from 1 to 9. So we can rewrite the original integral as the integral from 1 to 9 of, well, dx is du over 2. Okay, so we'll have 1 over 2, and we have the square root of u du. Okay, dx is equal to du over 2. This is u, it's in the denominator, so we get that. So we can factor out 1/2. We have 1 to 9 of u to the negative 1/2 power du. This is u to the positive 1/2, move it to the numerator, becomes a negative 1/2. Okay, so we integrate that. So you add 1 to the exponent, and you divide by the new exponent. And you evaluate that between u equals 1 and u equals 9. You see the 2 here cancels out with a half, so we just get basically u to the 1/2 evaluated between 1 and 9. So at the upper limit we have 9 to the 1/2 power, and we subtract out 1 to the 1/2 power. Well, that's the same thing as a square root, so you get 3. Square root of 1 is 1, so you get 3 minus 1, and so the area underneath that curve, which is the integral, is 75. That's 75. That's the problem number. The answer is 2. Okay, let's see, what else can we do here? 76. So the original integral, which represents the area underneath the curve x divided by the square root of 1 plus 2x squared dx, from x equals 0 to x equals 2. So we choose u equal to 1 plus 2x squared. Therefore, du is going to be equal to 4x. Take 2 times 2 is 4, reduce x multiplied by 1, 4x dx. You see we have x dx in the original expression, so x dx is du divided by 4. And then we're going to redefine the limits. So when x equals 0, u is equal to 1 plus 2 times 0 squared, which is 1. And when x is equal to 2, u is equal to 1 plus 2 times 2 squared. So 1 plus, that's 8. 1 plus 8 is 9. So we can then rewrite the original integral as du over 4 and 1/4 there. And then we have the square root of u. So we'll factor out, we change the limits here, so it's from 1 to 9. U equals 1 to u equals 9. So we factor out a 4. So we get the integral from 1 to 9 of u to the negative 1/2 power du. So we add 1 to the exponent, divide by the new exponent. We evaluate that between u equals 1 and u equals 9. So 4 times a half is 2, so you get 1/2 u to the 1/2 evaluated from u equals 1 to u equals 9. So we'll get 1/2. So u to the 1/2 is the same as the square root, so we get the square root of 9 minus the lower limit, square root of 1. So we get 1/2, 3 minus 1, which is 1/2 times 2, which is 1. So the integral, the area underneath the curve of this expression is equal to 1. So that's kind of interesting. Might want to look at that one just to see what it looks like. So I'm going to so what they're going to do here, okay, x divided by the square root of 1 plus 2x squared. And we want to go between 0 and 2. So there we go, that's it. Let me zoom in the x direction. So you can see in this direction we go from 0 to 2. And if we were to draw a line at 0.5, which would be about here, you can see that's probably about the average value of that function. So it makes sense that that is what's going on. Okay, this is problem number 77. So it's another definite integration, definite integral. So we have the integral from 1 to 9. Looks awful familiar. Let me just stop for a second. Okay, well, I guess I didn't work this one. Looks familiar, but apparently not. Okay, so we choose u to be the term in the parentheses. I think we actually worked this one in class, so if it looks familiar to you, just ignore it, but if you don't recognize it, then... Okay, so we change u as 1 plus the square root of x into 1 plus x to the 1/2 power. So du, the derivative of 1 is 0. The derivative of x to the 1/2 is 1/2 x to the minus 1/2 power, which is the same as 1 over 2 times the square root of x. And we add dx onto the end, which I forgot here. So we look at the original equation. You can see we have dx divided by the square root of x. So let's solve for that. Dx divided by the square root of x is equal to 2 times du. How did I get that? Multiply this by 2 to get that, and multiply that by 2. So for dx over the square root of x, I can put in that for, I can put 2 du. We have to redefine the limits. So when x equals 9, u equals, well, you go to what the expression for u is, which is 1 plus the square root of 9, which is 1 plus 3, which is 4. And for our lower limit, when x equals 1, u equals 1 plus the square root of 1, which is 2. So now we can rewrite the original integral. We integrate from 2 to 4 because now it's u and not x. And for dx over x, I can put in du over, or 2 du. So I get 2 du for dx over the square root of x. And for 1 plus the square root of x, I can put in u, so I get u squared. So I'm going to factor out the 2, and for u to the second power, I'm going to put in u to the minus 1 over u to the second power is u to the minus 2. So now we have a polynomial. So we integrate that. We add 1 to the exponent, which gives us -1. So we're not subtracting, we're adding. -2 plus 1 is -1. We divide by the new exponent, and we write down the limits of integration, which are u equals 2 and u equals 4. So now we can plug in the values of u, but I'm going to rewrite as u to the minus 1 is going to be equal to 1 over u. So I have -1 over u between u equals 2 and u equals 4. So we get 2 times 1 over 4, we subtract the same expression, negative 1 over u, but evaluating at the lower limit. We're sure we get this one. So you get 1/4 plus 1/2, which is 1/4. And so we get 2/4, which is 1/2. And that's problem number 77. The answer is 1/2. Remember, that's the area under the original curve. Okay, let's see, where am I here? 77, 78. Okay, let's do 78. Just pause for a second. Okay, so this is problem 78. And so what we have is the integral from 0 to 2 of x times the square root of, actually it's the cube root, isn't it? The cube root of 4 plus x squared dx. Okay, so not surprisingly, the quantity in the square root sign is u. So du is going to be, well, derivative of 4 is 0, so you just get 2x. And you multiply by dx. And you see we have, this is not x cubed, that's the cube root, so we have x dx. So let's solve for x dx. That's equal to du divided by 2. And we'll redefine the limits. So when x is equal to 0, which is the lower limit, u is equal to 4 plus 0 squared, which is 4. And when x is equal to 2, u is equal to 4 plus 2 squared, which is 8. So now we can rewrite the original integral as the integral from 4 to 8 of the square root of a cube root of u, and dx, x dx is equal to du over 2. Okay, before we integrate, we'll factor out the 2 in the denominator. And we'll rewrite the cube root as u to the 1/3 power. So we add 1 to the exponent, u to the 4/3. 1/3 plus 3/3 is 4/3. We divide by the new exponent, and we evaluate that between 4 and 8. So 4/3, dividing by 4/3 is like multiplying by 3/4. So we get 1/2 times 3/4 times u to the 4/3 between u equals 4 and u equals 8. So that's 3/8. And so we have 8 to the 4/3 power minus 4 to the 4/3 power. Now this one you can actually simplify because the cube root of 8 is 2 and 2 to the 4th power is 16. So that part is 16. How do I do that again? Okay, what that is, let me just do that off to the side here. 8 to the 4/3 is 8 to the 3rd, all raised to the 4th power. So when you have a fractional, when you have an exponent and you raise that to another power, you multiply them together. So 4 times 1/3 is 4/3. So if you take the cube root, cube root of 8 is 2, you get 2 to the 4th, and 2 to the 4th is 16. So that part becomes 16. This one is not so good because you really can't take the cube root of 4 and get a nice number. So it just ends up being, what would it be? You could say it's the the cube root of 4 to the 4th power, which would be 16 squared, which would be 256, I think. So let's see. 4 to the 4th power is 256. So that would be it. And what number was this? It's number 78. So what do we get? Yeah, they just did it in decimal form. So so you take 3 divided by 8 times the quantity 16 minus 256 raised to the 1/3 power, which is 3.619 according to the book. 3.619. That's the area. Probably could have just done it from this one. Just take 3 divided by 8, multiplied by the quantity 8 raised to the 4/3 power minus 4 raised to the 4/3 power, and I get 3.619. This is problem number 79. So we're looking for the area between x equals 1 and x equals 2 of x minus 1 times the square root of 2 minus x times dx. So this actually is one of those other kinds of integrals, because if I look at this and I make that u, this is not du. So let's plot this. So hold on just a second. I'm going to plot what this thing looks like. So let me stop sharing it, start sharing it. Okay, so the function is x minus 1 times the square root of 2 minus x. And I'm going to go between x equals 1 and x equals 2. So let me just zoom out, zoom in the x direction. So that's what it looks like. We're looking for the area under the red curve between x equals, actually we want to go from 1 to, oh yeah, it is 1, x equals 1 to x equals 2. And we don't have to draw vertical lines because it just corresponds with the x-axis at that point. So it's this area right in here. So let's bring that into the program. We're going to do an estimate. So let's see how close we get. Okay, so here we are. I'm going to take that. I'm going to copy it. And let's see here. Stop sharing that. Start sharing that. Okay, so there you go. And let's just put it on one page so we can see it better. So if I were to look for the average value of this function, what I'm going to do is I'm going to draw this horizontal line. And what I'm looking to do is to make this area here, so I'm going to do this, but then I'm going to undo it. What I'm trying to do is make that area equal to this area. That's visually what I'm supposed to do. And looking at it, looks like this green area is bigger than the blue area. So I'm going to undo that and then move this thing vertically. So that's making this area under here bigger and this smaller as I move this up. So of course, obviously that's too far. That's not far enough, so it's somewhere in between. And the average value is probably going to be, I'm guessing about here, which is that's 0.3, 0.25. So it's 0.25 times 2. So the area looks like it should be, the area is approximately equal to this height, which is 0.25, times the width, which is 1, which is going to be 0.25. So that's our estimate. Okay, so now we do our substitution. U is equal to 2 minus x. It's that term right there. So du is just equal to -1 times dx. So the derivative of this is 0 minus 1 derivative of x is 1, so we get minus 1 times our dx, so it's minus dx. So if we solve for dx, it's just going to be, if we multiply both sides by -1, we'll get dx by itself. And then we take this and we solve for x. So x is equal to 2 minus u. So using this substitution for here, this substitution for there, and this substitution for there, we can rewrite the original integral, but we also have to redefine u. So I mean the limit. So when x equals 1, what does u equal? Well, we just write the equation out. U is 2 minus 1, which is 1. And when x is equal to 2, u is equal to 2 minus 2, which is 0. So our limit's actually going to flip. We're going to go from 1 is our lower limit, because that corresponds with x equals 1. But our upper limit is 0. That's okay. It's no big deal. Okay, so now we're going to make all the substitutions. First substitution is the limits. So for the lower limit, instead of x equals 1, we're going to have u equals 1. For the upper limit, u is going to be equal to 0. For x, we're going to put in 2 minus u. So that's x. And then we subtract 1 more from that. Then we have the square root of u. 2 minus x is u, and dx is negative du. So what can we do? Well, we can factor out a negative sign. The term in the parentheses here is going to be 2 minus 1, which is going to be 1. And then we have negative u left over. And then we're going to have u to the 1/2 power times du. Now we could, this negative sign, you could actually get rid of that by just changing the limits. So we're going to change the u limits. And you can do that anytime. Anytime you have a negative sign, you can just flip the limits. So instead of going from 1 to 0, we're going to go from 0 to 1. And we might look at that integral later after we finish it all over, but finish it. For right now, we'll just leave it as is. We won't do anything. Okay, so then we multiply everything out. So we get u to the 1/2 times 1 is just u to the 1/2. And then u to the 1/2 times u to the 1st power. We add the exponents, and we get u to the 3/2 power. And we're going from u equals 0 to u equals 1. Okay, so we add 1 to the exponents, each exponent. So we'll get u to the 3/2 divided by 3/2 minus u to the 5/2 divided by 5/2. And that's our integration. So we take the integral sign away, but we do put this vertical line to say that we haven't evaluated the limits yet. We drop the du because that disappears when you add all those things up. So we get 2/3 u to the 3/2 minus 2/5 u to the 5/2. And we evaluate that between 0 and 1. So we get 2/3. The upper limit is 1. So we put 1 in for both terms. And then we subtract it, evaluated the lower limits. So you get 2/3 0 to the 3/2 minus 2/5 0 to the 5/2. Of course, that's just 0. So we'll get 2/3 minus 2/5, because 1 raised to any power is 1. And then what we'll do is we'll find a common denominator, so which is 15. So we'll take 5 times 2, which is 10, and subtract 2 times 3, which is 6, and we divide by 15. 3 times 5 is 15. So we get 4/15. And 4/15, let's just put it in decimal point, is 0.266. 0.266. Onward like that. Okay, so that is our actual area. And our calculated approximated area was 0.25. So obviously we got the right answer. So let's kind of review what we did here. Our initial integral we could not integrate. We don't have anything in it. It's not a polynomial. We can't multiply this thing out because it's not, can't do FOIL because one's the square root. So we chose this to be u. We calculated x from this relationship. So how did I do that? This went to the other side, became positive x. This went to this side, became negative u. So that was x. du, you take the derivative. Derivative of u is du. The derivative of this side is -1 times dx. So we get negative dx. So dx is negative du. We also changed the limits. So when x is equal to 1, we plugged 1 in. So when x equals 1, u equals 1. When x equals 2, u equals 0. So then we made all those substitutions. We changed the limits. And for x, we put in 2 minus u. We subtracted 1. We have the square root of u. We have negative du. So I factor out the negative sign. And I clean this up. 2 minus 1 is 1. Get the negative u. I changed the order of the limits from 1 to 2 to, 1 to 0, from 0 to 1. And then I changed that to a fractional exponent, multiplied it out so that I get 2 polynomials. I integrated those, added 1 to the exponent, divided by the new exponent. Plugged in 1. Ultimately, well, I took the reciprocal of these, so dividing by 3/2 is the same as multiplying by 2/3. Dividing by 5/2 is the same as multiplying by 2/5. And I plugged in the upper limit into the equation, and I subtracted, plugging 0 into the equation. I got that. I simplified it, got the right answer. But the one thing I want to do is to go back to this point right here and add a page. Well, actually, I'm going to do the graph of that particular thing. So I'm integrating 1 minus u. Pen's not working here. Oh, there we go. 1 minus u to the 1/2 between 0 and 1. So what does that mean? Okay, let's go look at the graph of that and show that it's the same thing. So this is the original function. The transform function was 1 minus u, but I can use x because it's just a name of a variable, times the square root of x. So that is the new integration, and I go from 0, u equals 0, to u equals 1. So I graph that. Looks just like the same thing, except it's the other way around. It's kind of like an airfoil. So, so obviously, since it's the same shape but backwards, I would do the same thing. Let me just get a camera. Grab it in there. And now we'll go back to Smartboard. And all I'm going to do is just move that thing to layer on. And that's my new graph. That's my old graph. You can see that transformation just flips it around. So obviously this area is going to be the same as that area. So I don't even have to think about it anymore. Okay, well apparently I forgot to push the record button and the talk button. So anyway, this is problem 71. And this is the other way of doing it, where you change the limits and you don't have to substitute back in. So let me just explain what we did again. So 71 had this problem.
We chose u to be determined in parentheses. We calculated du. We solved for what we had in the problem, which was x dx. So that was du over 2. If you make the substitution, you will get this equation. But even before we do that, these are the limits of integration in terms of x. Well, you can figure out what the limits are in terms of u by just using this equation here, plugging in the upper limit, getting the corresponding u upper limit, and put in the lower limit and get the corresponding u lower limit. And if you do that in this case, you'll get negative 1 squared plus 1. That's the lower limit here, negative 1. You get positive 2. And if you put positive 1 in, you get positive 1 squared plus 1, which is also 2. So it turns out these are actually the same numbers. And one of our rules about integrals is if you have the same limits, the upper and lower limits are the same, the integral is 0. So you could actually just say it's 0 straight off from that. It doesn't always happen. I mean, that's kind of unusual to happen in u substitution, but it happened in this particular case. So the other way, if you wanted to go ahead and just show how you would go through this when you don't have the same limits. So I'm going to go ahead and just pretend they aren't the same limits. And ultimately, it will go to 0 anyway. But if these were different or if they're the same, you can still do this. So we take 1/2 divided by 4 is 1/8. We put in the upper limit, u to the 2 to the 4th power. We subtract the lower limit, which is 2, and raise that to the 4th power. And these turn out to be the same, and so they go to 0, and you get 0. But this only works if these two numbers are the same, which doesn't usually happen. The advantage of doing this kind of substitution is that once you make the substitution limits, you don't have to go back and plug u back in and get it in terms of x. So it's one less step. And typically this equation is easier to evaluate than the one when you put it back in. I'll probably do half one way and half the other just so you get used to both ways. Okay, this is problem 81. So it's a trig function. So we're integrating the cosine of 2x over 3 times dx. So the argument of the trig function is not just x, and I forgot x. I put pi in there. I don't know why I chose pi. Okay, let me fix that. So you get 2x over 3. Okay, so you pick the argument of the trig function to be u. So du is the derivative of this. Well, the derivative of x is 1, so we get 2/3 times 1, and then we multiply by dx to get it in the proper form. So what do we have? We just have dx by itself. So dx is 3/2 du. Okay, so 3, since we don't have any adding or subtracting, it's all multiplication, we can say this is in the denominator on the right-hand side, so we can move it to the numerator. So the 3 comes up there, and the 2 goes down there, so we get 3/2. Or you can just think that you multiply this by 3/2. 3/2 times 2/3 is 1 to solve for dx. That's dx. This is x, and then we have to change the limits. So when x equals 0, u equals 2 times 0 divided by 3, which is 0. So u equals 0 means x equals 0, and when x equals pi over 2, u is equal to 2 times pi over 2 divided by 3. So I'm just plugging in pi over 2 for x. So the 2's cancel out, and I get pi over 3. So I can rewrite the original integral, including the limits, as the integral from 0 to pi over 3 of the cosine of u times, what is dx? Dx is 3/2 du. Okay, so we have the cosine of u times 3/2 times du. So we factor out the 2/3. So we have the integral of the cosine of u du. We go to page 250, and we say, okay, what's the integral of the cosine of u du? It's the sine. So we get 3/2 the sine of u,
evaluated between u equals 0 and u equals pi over 3. So now what we do is we just take our constant, multiply it by the sine of pi over 3 minus, so that's plugging in u equal that at the upper limit, and then we subtract it at the lower limit, which is 0, sine of 0. So we don't subtract the lower limit, we subtract the function evaluated at the lower limit. So we get 3/2. The sine of pi over 3 is the square root of 3 over 2. And the sine of 0 is 0. So we'll get 3 square root of 3 over 4, and that's the area. We're trying to find the area. That's what definite integrals do. So 3 times the square root of 3 over 4. And let's just multiply that out. See what we get number-wise. 3 times the square root of 3 divided by 4. It's 1.3. 1.3. Yeah, it's very close. 1.299. Okay, so that is the area. Let's plot that original function. So we're going to open up that, and we're going to share it with you. Okay, so the original function was the cosine of 2x divided by 3. And the limits were from 0 to pi divided by 2. Okay, let's zoom in here a little bit. Okay, let's take a picture. Let's make sure I have something to take a picture on. Okay, so now we're going to make an estimate of what's going on. So that's our curve. That's the original curve. If I take my blue line, and I draw this horizontally, obviously that's the area under the blue rectangle is greater than the area under the red curve. Here, of course, it's too small. So somewhere in here, I'm going to look at these two, and I'm going to say about right there, that this area is about equal to that area. I think maybe closer to there. Okay, so what is that area? The area, the rectangle, is going to be 1.57 probably. 1.57, that's the width. And the height is 0.758. And this is 0.7585995. So those are, I don't know how many, 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay, so each one's 0.05, so that's 0.82. 0.82. And if we multiply those two together, 1.57 times 0.82, we get 1.29. 1.29 is the area that I estimated. And I estimated it by drawing this blue line so that I have this area above the blue curve, below the red curve, and I have this area the other direction, and I eyeball them so that they're about the same. And this again is your average value, so that the area under the rectangle is the same as the area under the red curve. Okay, and you just be amazed here about how close I am. Okay, so my approximation was 1.3 versus 1.29, which is within less than 1% error, so that's pretty good.